So good morning, everyone. Today, we will be discussing macroscale momentum balances as they apply to fluid flow systems, which hopefully for those that have yet to jump into the homework will find extremely helpful. So macroscale momentum balances. So we can recall from physics that momentum is simply a mass times a velocity. And when I'm interested in the change in momentum of a system with respect to time, what I'm really looking at is the derivative of the product of mass times velocity, which by the product rule, I can write out as mass times the change in velocity with respect to time, plus velocity times the change in mass with respect to time. Which means when I'm looking at a momentum balance and I'm considering how momentum's changing in my system, I can be looking at mass with respect to a change in velocity or an acceleration plus a velocity with a change in mass with respect to time of my system, which I consider it being a mass flow rate at a certain velocity. And so what this tells me is that if I look at a momentum balance, I can state that my change in momentum in my system at any one time is a result of acceleration, or what I would consider forces acting upon my system, resulting in whether it having a net acceleration of my system or not, as well as flow or convective flow acting upon my system. And so what that means is when we're looking at momentum balances, which I can also write as momentum in minus momentum out, plus or minus, or I just saw plus, the sum of any forces, m dot, which is essentially dm dt. I'm looking at forces, once again, and any sort of flow associated with my system. And so what this is really meaning is that when we're looking at macroscopic momentum balances within a fluid flow system, momentum can be transferred via convective flow or forces acting upon our system. So let's look at an example of how we can analyze a system in terms of momentum balance. So this is flow through a pipe. So if I have flow through a pipe, then assuming this is my flow direction, I can state that I have some pressure at the inlet, some pressure acting on the outlet. I can also define my system being this kind of box here, or this section of the pipe. And I also have another force within the system, which is resisting that flow, which mainly occurs along the walls of the pipe, and that being shear stress, which I denote tau sub W, which is shear stress along the pipe wall. Now, if I assume the positive x direction is to the right, I can define a momentum balance in terms of the forces in convective flow that's happening in this system. And so for this system, one of the forces I have is initial pressure and my final pressure, so P1 minus P2. And since I'm interested in terms of a force, since pressure is a force over an area, to get the simple force, I multiply it by the area on which it's acting, which for this system would be the cross-sectional area, or I can simply say pi d squared over 4. Now I also have momentum as a result of mass flow in at a certain velocity and mass flow out with the same velocity. Which if I wanted to write my mass flow, it would be rho times u times a. So I would have rho u squared times a. Now the mass flow out is going to result in a negative momentum when I have one more term, which is looking at the shear stress on the system, which since it's going to act opposite my flow and opposite what I've defined as a positive direction would be negative tau w, and it's just like pressure, I have to consider what area it's acting upon, which for this system is going to be the surface of the pipe, or pi times d times L. And this is going to equal the change in momentum with respect to time. Now, since I'm looking at a simple flow through a pipe, and if I assume the pipe's not going to be moving, we're not going to get any sort of net increase in momentum, and it's at an equilibrium, I can state that as 0. And so let's take a breakdown of each of these systems. So this is the pressure, force. Then we have our shear stress, force. And then we have convective flow, in and out of our system. So this describes essentially the momentum inputs, outputs, as well as forces acting on our system, which is this section of our pipe. Are there any questions on how I was able to look at the system, identify these forces and these convective terms, and how I've organized it? I know I might be going a little fast, so I want to stop here and give you guys an opportunity to ask questions or request some clarification.
Dr. Lopez?
Yes.
Could you explain why momentum out is negative?
Sure. That's a good question. So if I'm looking at my system, the flow coming in is bringing mass in. And so with that, it's adding mass in a certain velocity into our system. However, if we look at the mass flow out, it's taking mass and velocity out, which means it's taking momentum out of our system. And so by that convention, since it's essentially taking momentum out of our system, it comes out as negative. The way I like to think of it is, if you're in space and you're throwing, rocks or debris, that's going to be robbing yourself of momentum in that direction. And so the actual result on you, if you're the system, is in the opposite direction. Does that clarify it?
Yeah, that makes sense.
Okay. All right, so since my mass flow and mass flow out are the same, there's no result change in momentum by flow, which we should kind of expect, which means that in order for this system to not move, the shear stress and the pressure difference or pressure drop have to be related such that these forces balance, which means I can say P1 minus P2, which for simplicity terms, let's just call it delta P, times pi d squared over 4 has to equal the force resulting from shear stress. Which means if I want to solve for shear stress, I just divide by pi dl, and I'm left with delta P times diameter over 4 times L. And what this tells us is that shear stress results in our measured pressure drop in convective flow. So essentially, we lose our momentum and we lose our pressure during flow as a direct result of the shear stress which is exerted on our system. And we can quantify that by simply measuring the constraints of our system and the pressure drop itself. So keep this in mind. We're gonna look at that probably next week when we start calculating influences of flow and how friction comes about, because the shear stress is going to be a major factor in determining frictional pressure drop in flow systems.
Hey, Dr. Lopez.
Yes, sir.
Would this equation still be valid if the diameters were different at both ends?
That's an intriguing question. If the diameters were different at both ends, this would be a lot more complicated, primarily because, well,
I guess you'd have your momentum
the
both going to
momentum,
0.
well, momentum would be 0, but the shear stress and there would be more to the expression. It wouldn't condense as simply as it does here.
Yeah, that makes sense.
Primarily because in that system, your mass flow rate in and out would be the same, but the momentum in and out would not be.
Right.
And so what that's going to tell you is that the expansion and contraction in your flow would also contribute to the pressure drop, which we will talk about next week when we discuss fittings and how flow expansion and contraction results in additional frictional dissipation. And that's basically what we would see from that, is that we would have a second term that describes pressure drop and also that describes shear stress.
Right. Okay. Thank you.
You're welcome. Let's look at another example. And here, I'll pull up the image so you can see what we're talking about. So hopefully you see this. So let's look at this system. And hopefully you see my PowerPoint now, where we have a jet that is being ejected from a pipe. So it's a jet of fluid, and it's striking this trolley coming in at a velocity of u, and it's causing the trolley to move forward at another specific velocity, v. So the question becomes, how can we write a momentum balance on the trolley shown, which is moving due to the momentum transfer applied by the water jet? So let's go back to our note taking and see what we can come up with this expression. As always, I always recommend draw your systems as much as you can or as good as you can. So in this system, I also like to define my system. So for this system, we've got the trolley coming in as our system. It's moving with some velocity v. I also have a pipe here that's resulting in a jet striking the trolley with a velocity u. And so what this should be kind of indicating to you is we have two different velocities in our system as a trolley, which means our system is moving. And so since we have multiple vectors and a system and a system boundary that's moving with one of those vectors, the concept of reference frames becomes extremely important in defining this momentum balance. And so there's a couple ways in which you can define it. You should end up with the same solution. However, for this example, we're going to be looking at and assuming that that control surface is moving with the trolley, meaning my system boundary is going to be moving with the trolley. And so we're looking at another momentum balance. But for this system, our momentum balance is not going to be equal because the trolley is moving. Primarily with, in a sense, that vector v can and will be increasing. And so the question is, how do we quantify the acceleration as a function of the flow rate of the jet and the two relative velocities? And so if I consider my initial, just really generic momentum balance, momentum in, momentum out is a result of the momentum accumulation, I can ask myself, is there momentum in? Is there momentum out? And is there a net accumulation of momentum? And so for this problem, there is momentum in because we have the jet striking the trolley. Here, I'll use a different color. Sorry, I keep switching back and forth. I know it's probably a little obnoxious. So we have the jet striking the trolley. We don't really have any momentum out. And we do have accumulation because we have acceleration of our trolley. And so we can ask ourselves, well, if the momentum in is the jet striking the trolley, that's that force, then we have the density of the trolley, the velocity of the jet, and the acceleration, and then the net velocity or the net momentum that that jet is bringing to our system, which would be u minus v. And it's hard to understand why it's u minus v, but if you consider if the jet was moving with the same velocity v, then there's no way for that water to be entering our system. So the essential momentum addition would be 0. And so the jet ceases to be relevant when the trolley moves at the same velocity as the jet. And so if that's our if that's our net mass momentum in, then we consider, well, what's our accumulation or our dm dt? Well, I also like to write dm dt as a mass times change in velocity with respect to time plus a velocity times respect to mass. It should be a v with respect to time. And so it's v because our system is the trolley and it's moving at a velocity v. So dv dt is simply acceleration because it's just a velocity shifting with a change of time. The change in mass, we have to consider, well, what's the mass flow rate being added to our system? Well, and what the trolley sees, it's going to be, once again, looking at that reference frame, rho a u minus v. And so what we have when we combine these concepts is rho a u minus v equals the mass times acceleration plus rho a u minus v times v. So if I distribute this rho a u into the u and the minus v, I have rho u squared a minus rho u v a equals mass times acceleration plus rho u va minus rho a v squared. So it looks a little messy, but if I basically put everything on this side of the expression, what I'm left with is rho u squared a minus 2 rho u v a plus rho v squared a equals mass times acceleration. Now the good news with this term is I can factor it up such that this simply becomes rho a u minus v squared. And that tells me my acceleration, simply rho a over the mass times u minus v squared. So I'll take a second. We'll walk through that one more time. And like I said, I'll open it. I want to make sure you guys kind of get a loose understanding of what we've done. So for this example, we're looking at the essential momentum balance around this trolley as it's being moved forward, or it's causing an acceleration because we have water striking it with a certain velocity u. Since this jet is causing the trolley to move forward at a certain acceleration, we can consider that the momentum, or the net momentum of our system, is not zero, such that we have momentum being added to the system by the jet, which is resulting in a net acceleration of our system. The jet striking the trolley is bringing momentum in by this term, rho ua times u minus v, and the acceleration, the accumulation of the trolley, is quantified by the mass times acceleration plus the change in mass that we see at that velocity. Putting these terms in, we can do some mathematical rearrangements such that we can solve for our acceleration as a function of the fluid density, the area of flow, the mass of the trolley, and the relative velocities of both the jet and trolley respectively. So does everyone kind of have an understand how I was able to look at that system, identify what terms are critical for the momentum balance, quantify those terms, and then solve for the acceleration?
What is our difference between this lowercase a and the uppercase a?
Lowercase a is acceleration, uppercase a is the cross-sectional flow area of the jet. And this system can also be analyzed if you're not considering the fact that that system boundary is moving with the jet. However, it makes the setup a little more complicated. So for this systems, when we're looking at objects, I usually like to have the system following the object and not that of an observer. However, you will still arrive at the same solution. Any other points of clarification that I can make? I'm more than happy. All right, if not, let's take a look at another example. This one, we're looking at just a simple water jet striking a fixed vertical plate. The diameter of the jet is 10 centimeters and the velocity of the jet is 15 meters per second. What is the force of the jet acting on the plate? And so for this one, I'm going to give you guys a couple minutes to work together in some breakouts, just to get you guys talking and doing some calculations yourself. So feel free to jot this stuff down, then jump into a breakout room and work together. All right. So we're looking at here. It's just water striking a vertical plate. The diameter was 10 centimeters, 0.1 meters. The velocity was 15 meters per second. So what did you all arrive at for the force
I
of the
got
jet?
1,770 newtons, or somewhere around that number.
All right. Which should have simply been the density times velocity squared times area, which for this system was 1,000 kilograms per cubic meter times 15 meters per second times pi times 0.1 meters squared over 4. All right. So that should have gotten you about 1770. Yeah, that's pretty close. Let's look at another example that's a little more complicated. In this example, we have a reducing elbow through which water is flowing in at 6 feet per second with a pressure of 3 bar. So the question is, identify the retaining forces necessary to hold the elbow in place, assuming the inlet diameter, or d sub A, is 2 inches, and the outlet diameter, d sub B, is 1¼ inches. So, as always, the first thing I always like to do, draw out our problem. So for this system, we've got a reducing elbow where diameter 1 is 2 inches, diameter 2 is 1¼ inches. For this system, I'm going to consider both pressures on the inlet and outlet are going to be about the same, which is 3 bar. And did I say anything about my velocity? It's coming in at 6 feet per second. So, as always, let's define our system. Our system for this is going to be the elbow itself. And we also have some mass, 0.7 pound mass of the elbow itself. And so we're looking at retaining forces such that there's no net movement, or dm dt is going to equal 0. So this can be drawn up like a force balance, where you can analyze it in both the x and the y direction. So if we're going to look at an x force direction force balance, assuming that both to the right is positive and up is positive. So what forces do I have in the x direction in this problem?
You'd have the velocity, or the force of the velocity of the movement going.
Yeah, so we
See
have the
that?
force of the convective flow. Would that be in the positive direction or the negative direction?
It would be positive.
All right, it would be positive. So we have the mass flow rate in with its velocity. What other forces do we have involved currently in this x direction?
Is there shear stress on the pipe?
There would be, but for the way I'm looking at it, I'm gonna neglect it. I'll be honest. That's a good question. And surprisingly, no one's asked that in the 4 years I've taught this. So good job.
You have the pressure acting on the inlet.
Yes, all right. So we also have the pressure. Is that gonna be in the positive or the negative direction?
Positive.
So it'll be in the positive direction. All right. And is that all we have? The last thing we're going to have is our retaining force, which since these are both in the positive direction, I'd assume the retaining force is in the negative direction, such that our system balances. So now with that in mind, we can directly solve for this retaining force in the x direction. And so the mass flow rate in, if we're looking at water in this system, it's the density of water, or 62.4 pound mass per cubic foot, times the velocity, which since it shows up twice, I just say the velocity squared, 6 feet per second squared, times the flow area, which is pi times 2 inches over 12 feet squared over 4. Then I can consider the pressure, my next term, which is, in this case, 3 bar. But I want to convert that to my English units that I have. So when 1 bar is 14.5 pound force per square inch. And now I need to convert my square inches into square feet. So I have 140 square inches and 1 square foot. And then I have my area, which is pi times 2 over 12 feet squared over 4. One thing I forgot to look at here is on my mass flow rate in, I'm still looking at pound mass. And so I have to convert that into pound force. And I can do that simply by dividing by G sub C, which I'm out of space. Crap. I'll squeeze it in here, even though it probably isn't going to look pretty. 32.2 pound mass foot for pound force second squared. And I can do a quick unit check just for everybody's benefit. So this gets rid of the pound mass. I have second squared here. That goes away. I have, let's see, feet to the 4th on top, and then I have a cubic foot here and then a foot here, so all the feet disappear, and I'm simply left with pound force. So I have pound force there in this term. My bar goes away, the inches squares go away, and the feet squared goes from here. So I'm left with pound force here. So this leaves me with my F in the X direction in terms of units pound force, which is what I want. And I can say minus Fx equals 0. Add everything over, and I say Fx is equal to approximately 138.2 pound force. Or if you want, you can just say to the left. Any questions on that?
When you mentioned that the force is going to be to the left, is that going to be, if we go back to the diagram, is that going to be toward the left or to the right? Well, because it looks like to the right, it's going to be putting its force against the wall of the pipe.
I mean, it would be to the left. So Fx would be like this.
Okay. Yeah. Oh, yeah. Now I see what you mean.
Yeah. So like I said, you can put the negative there if you want. You could tell me to the left if you want. Just either or is fine with me. Signs are confusing and relative. So as long as you know what they mean, I'm fine in terms of your solution. All right, now let's look at the y direction. So for this system, what forces do we have in the y direction?
Would we have gravity apply here?
In this case, yes, we would have gravity. So mass times gravity. And it's going to be negative because gravity is always in the down direction. Darn gravity. What other forces do we have acting on this system?
Wouldn't we have the same force of the flow as we did in the x direction?
We do have the same flow. It would be mass out times velocity out, which is going to be in the y direction because it's leaving our system. And then we have pressure as well, and it's also going to be on the negative y direction, which means our y direction retaining force has to be in the y direction if our elbow is not going to move. And so what we have here is 0.7 pound mass times gravity, which is 32.2 feet per second squared. But that gives us a bunch of pound mass units that we don't want. So 32.2 pound mass feet per pound force second squared, which really just tells us that that pound mass is also pound force. Then we have our mass flow rate out, which is 62.4 pound mass per cubic foot times the velocity squared, which since this is the smaller outlet, the velocity is higher. If you do that math with the continuity equation, you get about 15.4 feet per second squared. Then you get the area, pi times 1.25 over 12 feet squared over 4. And then you have to divide by g sub c, 32.2 pound mass foot per pound force second squared. So this is negative, that's negative. The last term we have is our pressure, 3 bar times 1 bar, which is 14.5 pound force per square inch. Then there's 144 square inches in a square foot. And then we just multiply it by our area one more time, 1.25 divided by 12 feet squared over 4. Plus Fy equals 0. I'll zoom out so you can see it all. If we do all that math, we should find that Fy is equal to approximately 53.6 pound force. So now we have our force in the x direction, our force in the y direction, it's positive or up, if you'd like to designate it that way. And if we wanted to find the total force, resultant, simply the square root of the x and the y values squared, which if you do that math, you should get, I can't remember off the top of my head. Drast, how dare you, Dr. Lopez, not know all these numbers by heart. Let's see, what was x, 138.2. You get about 148.2. Any questions on that example? You're going to have a homework problem pretty similar to this one. So it's definitely worth understanding how I was able to identify the necessary forces and do the calculations, because it is very unit heavy, it being the English units. All right, if not, we might have time to squeeze in the last problem for the day, which is looking at this system of a rocket with a mass big M in pound mass, with a vertical velocity at any instant of v, and a propellant is being ejected downwards through the exhaust nozzle with a mass flow rate m, which in pound mass per second, with a velocity u relative to the rocket. And so the question is, with this system, we also have not only gravity resisting motion, but also a drag force. So the question asks to identify the momentum balance in order to get an idea of the rocket acceleration, which is also designated dv dt. So for the sake of time, I'm gonna skip the option for us to kind of break out and let you guys think about it. I'll just kind of show you a walkthrough of how this one can be solved. So example, rocket acceleration. So for this system, we've got our rocket. It's important you draw it. And we'll judge your ability to draw the rocket. So we've got gravity. We've also got drag. And we've got the propellant moving us forward, which is not really a force, it's mainly that convective momentum addition. So in this sense, since we know that the system's accelerating, we know that our dm dt isn't zero. So we can quantify the forces in the convective flow. Gravity is going to be that big M minus G in the negative direction. The drag force is going to be in the negative direction. The momentum addition via flow is going to be in the positive direction, and it's going to equal our dm dt. Or once again, m dv dt plus v dm dt, which in this we can call acceleration, and the mass we're essentially gaining or losing in this system, we're actually losing, which is our negative mass flow rate of our propellant. So what we have is negative big mass times gravity minus our drag force plus our mass times velocity minus mass times v equals big mass times acceleration minus m dot times v. Looking at this, since the m dot times v shows up on both sides, we can neglect it. So we're left with big M times G minus K V squared plus little m times u equals mass times acceleration, which means acceleration is just divided all by the m, and we're left with negative G plus the quantity mu minus kv squared over big M. And so that's our acceleration, which means we gotta be getting that propellant on a reasonable flow rate and a pretty good velocity to overcome both gravity and our drag force to get reasonable acceleration.
One quick question regarding this problem, which is what is K?
K is a proportionality constant that relates the drag force to the flow velocity. Because when we look at drag force, it is directly correlated with the square of a fluid velocity. We will talk about flow past objects probably in 2 or 3 weeks, where instead of looking at K, we'll actually define what K is. But for the sake of this problem, and for simplicity's sake, we can just say it's a constant. We'll talk about what that value can be.
Okay, I just asked because we have a homework problem involving calculating drag force, and I don't believe it provides us with a K value. So I was just gonna ask about
In this
that.
class?
Yeah, homework 3, I believe.
Let me
It
take
can
a
be
look.
solved using the mechanical energy balance.
It doesn't give us an area of the plane in question 1. That's the only thing I was going to ask about too.
I think it's this one is you're looking at a force balance, and since it's steady flight, the momentum balance has to equal out.
Okay.
And so you're not really looking for the nitty gritty in terms of what quantifies the drag force. You're really looking for, when you set up your force balance, one of the terms is going to be drag force, and it should be the only one you don't really have. And since it's balanced by the other forces, what's left is the drag force. Does that make sense?
Yeah, that makes sense.
Yeah. All right. Any other last minute questions? We're about out of time, but fortunately we got through the fairly large discussion on momentum balances. I know we kind of moved quickly just due to time considerations and that we are a little behind moving through some course topics. But one thing I will say is I would definitely spend some time studying and reviewing momentum balance concepts, because it gets really tricky and difficult to mentally conceptualize and grasp. I don't expect you on the first try on a lot of these problems to be able to just look at the system, come up with the equation and solve. That takes some practice. So I encourage you all to practice, because these are the types of problems I like to put on a midterm final, because it's less math intensive and more concept mastery in terms of testing your ability to understand and grasp and apply the concept. So like I said, don't be surprised to see this on a midterm. So with that in mind, are there any other further follow-up questions and points of clarification that I can make? All right, if not, take care, guys. I hope you have a great day and a wonderful weekend. Also, I did send an email this morning that I'm not going to be able to do office hours, unfortunately, today at 11 and 1. I will be on from 3 to 4 for that purpose. So if you have questions, send me emails or drop by around then. I apologize for the last minute notice, but it gets tricky as we get into the semester, me trying to corral people and touch base with certain folks at the university. So if not, take care, guys. Have a great weekend, and thanks so much for attending.
Thank you.
Thank you.
All right, take care.
Thank you.